Hello. So today again I will continue this topic of diagonalization. So so in the diagonalization you have a matrix A. So for example, this one, okay, and then you convert that matrix into P D P inverse, P D P inverse, okay. So uh, when we convert that matrix into PDP inverse, we can also see that if, for example, if we take this expression as A and then we multiply on the right, we multiply both sides by P. So then what we get? AP, okay, AP and then PD P inverse, okay, and then P, okay. So we have added on both sides, we have multiplied on both sides by P. Uh, Here we get from the, on the right hand side, we have P inverse P. So PD, P inverse P, P inverse P is the identity matrix, okay? And, but we know that any matrix, for example, PD is a matrix, okay, will be multiplied by the identity matrix will be the same matrix. So it will be PD. In this case, if we get an expression AP is equal to PD. So in this expression, we can see that there is no P inverse involved over here. So if the question, so for example, if the question is diagonalize, okay, diagonalize A and verify. So what you are going to do is you will diagonalize A, which means you will find P, D, and P inverse. And then for verification, you will multiply P with D and then with P inverse, and then both sides should be equal to, both sides should be equal. So an alternative way for verification is this, okay, AP is equal to PD. So what is the difference between this and in the previous case? If for example, if you say that if you can find A, if you can diagonalize, so normally you will find the diagonal matrix first, and then from the eigenvectors you will find the P vector. And from P vector, we will apply the procedure to find the P inverse. So in this case, for example, if you want to verify your answer without finding P inverse, okay, without finding P inverse, so you can do the verification by this. So then what you can do is you will multiply A by P, and then you will multiply P by D. Okay, both answers will be same. So that will be also an alternative way for your verification. So in this case, you can skip the process for finding the P inverse. Okay, so maybe in this process it will take less time, or yeah, because maybe in this process it will take less time because you will do some process for finding P inverse from P, and then you will be doing those multiplications for the verification purpose. But in this case, the alternative way for the verification is also that you can do, you can find, so in this case, for example, process one, okay? Okay, so process one, you will have, you find D first, then find P, then find P inverse, okay, and then verify, okay, then verify by multiplying P P with the D and then PD with P inverse, okay. So 1, 2, 3, 4, 5, a 5-step process in this case, in the process 1. But in the process 2, so you will find D, you will find P, and then you will not find P inverse. So you will verify by multiplying A with P, by AP and PD. So this is a much quicker process, okay? So in both cases, you can verify the answer, okay? So this is one point which I want to say. Another point which I want to emphasize over here is that when there may be some situations when finding the P matrix, okay? So you remember that you find the P matrix, from eigenvectors, okay, in eigenvectors. So when we find the eigenvectors, then you have the augmented matrix, something like this. Okay, so you have some value over here. So I'm just taking a 3 by 3 case, okay? And then on this side, you have 0, 0, 0. And then sometimes you may have some matrix, something like this. So you may have some value over here, maybe some value over here, some value over here, some value over here, some value over here, some value over here. Sorry, the last one will be 0. Yeah. So in this case, yeah, I mean, you may have a case something like this, okay. So a value over here, and then you may no, in this case the last one will be 0. So the special thing to note over here is that the whole column will be 0 in some situations, okay. The whole column will be 0, but otherwise you may have some values over here, maybe 0 over here also, okay. So for example, if you have a matrix something like this, let me show you. If you get when finding the you get a matrix something like this, after after you reduce it to the echelon form, okay, after you reduce it to the echelon form, you get a matrix like this. So for example, if you get a matrix like this, so 1, 0, 0, 0, 0, 1, and then you get 0, 0, 0. So here you can see that, okay, last row is 0, and so last row is 0, okay, in this case. But in addition, the second column is also 0. And if your identity matrix, if your eigenvector is, say, for example, U1, which is which will be of 3 components, say, I don't know, maybe K1, K2, K3, okay? It has 3 components. So these 3 columns 1, 2, 3 correspond to K1, K2, and K3. Okay. So in this case, from the last row, everything is 0. Okay. In the second row, what you get is, from the second row, what you get is K3 is equal to 0. And from the first row, we get K1 is equal to 0. Then what is K2 in this case? Okay. So here we can make some mistake by assuming that K2 is also 0, but this is not true in this case, because whatever the value of K2 we will put, it will satisfy this equation because the coefficient is 0 over here. So for example, this equation is something like this. It is 1 times K2, K1 plus 0 times K2 plus 0 times K3. So is equal to 0. So here we have already found that K1 is 0 and then K3 is 0. But with K2, we don't know. But we can put any value of K2 over here because it will still be multiplied by 0. So therefore, K2 does not necessarily have to be equal to 0. So K2 will be an arbitrary value, arbitrary constant. Okay, K2 can be an arbitrary constant. So in this way, then we can represent this U1 matrix as because K1 was 0. K2 will be an arbitrary constant. Maybe we can say that arbitrary constant is S and then 0. And then we can take S out. So it will be 0, 1, 0. Okay, 0, 1, 0. So in this case, the eigenvector corresponding to this situation when one whole column is 0 will be 0, 1, 0. Okay. It's not 0, 0, 0. If it will be 0, 0, 0, then that will be wrong. Okay, that will not be an eigen vector. 0, 1, 0 will be the eigen vector in this case. So this thing you should keep in mind. Okay. So I especially mention this thing so that if you come across this type of situation, you can handle it correctly. Is it clear?
Yes.
Yes.
Okay, so then let's do some more examples of this. So suppose if we have a 5 by 5 matrix. Okay, we don't know what is that matrix is, but we know the we know for 5 by 5 matrix there will be 5 eigenvalues. So we know the eigenvalues. Okay, so eigenvalues are -3, 1 by 2, 1, 2, and 4. Okay, we know the 5 eigenvalues, but we don't know the what is the matrix. So then can we find the determinant of this matrix? Okay, so suppose the matrix is A. So can we find the determinant of this matrix A? So the answer is yeah, maybe we can try. Okay, so since we know that eigenvalues are, since we know that for we have these 5 eigenvalues. So all eigenvalues are different. They are not repeating. Okay, so -3, 1 by 2, 1, 2, 4. So they are not repeating. So it means that this gives us the indication that matrix A is diagonalizable. That is we can diagonalize this matrix. So because the values are different. Okay, the values of the eigenvalues are different from each other. They are distinct eigenvalues. So This gives us the surety that matrix A can be diagonalized. Okay. So once it can be diagonalized, so then we can write this matrix as A times P times D times P inverse. Okay. Here, what we have now is D. Okay, D is the diagonal matrix, and for we remember from the properties of the properties of the determinant, properties of determinants, that for upper triangular or for lower triangular or for that case even the diagonal matrix, the determinant of the matrix of a diagonal matrix, okay, from the properties of the determinant of if diagonal matrix is equal to the multiplication of the elements on the diagonal. Okay, so this, which will mean that the determinant of this D will be equal to minus 3 times 1 by 2 times 1 times 2 times 4, which is equal to 2 cancels this 2, so it will be minus 12. So we can find from the properties of the determinant that the determinant of diagonal matrix will be 3, will be minus 12. Okay, because a diagonal matrix is is an upper triangular or lower triangular. I mean, it is both the upper and lower triangular and plus. So for that kind of matrix, the determinant is equal to the multiplication of its diagonal elements. And you know that the diagonal matrix is the one in this case uh, which places the eigenvalues on the diagonals. So the determinant of D is minus 2. So what we need to find is determinant of A. So determinant of A will be equal to the determinant of P, D, P inverse. And from the properties of the determinants, we know that this is equal to the determinant of A into the determinant of D into the determinant of P inverse. And from here, we know that the determinant of P inverse, sorry, this will be P. So determinant of P inverse is equal to the 1 over of the determinant of P. So this is the determinant of D, and this is the 1 over the determinant of P. So now determinant of P cancels with determinant of P. So what is left is determinant of D, and we already know the determinant of D, which is minus 12. So it means that in this case, the determinant of this matrix A is minus 12. So which means that if a matrix has distinct eigenvalues, its determinant will be the multiplication of those eigenvalues. So here we can find about that. Okay, is it clear?
Yes.
Okay, so one more question. Example. Find a 3 by 3 matrix. Find a 3 by 3 matrix whose eigenvalues are minus 3, 4, 4, and associated eigenvectors are associated eigenvectors are these three eigenvectors: 1, 1, 0, 1, 2, minus 1, and 1, 3, minus 1. Okay, so we need to find A. So in this case, first of all, we can see that two of the eigenvalues are not distinct. Okay. However, we can see that the eigenvectors they are actually independent with each other. So a general inspection shows that we cannot get, for example, from this matrix the other vector and by any multiplication. So, for example, if it is 1, then it is 1. So from 1 to 1 we will multiply by 1, but then we cannot get this second element from here. So these two first matrices vectors are independent with each other. And similarly this one is to 1, and then from you cannot get 2 into 3. So all these three vectors are independent with each other. So since these are independent vectors, we can say that they form a basis in R3. So it means that our matrix P will be, in this case, 1, 1, 0, 1, 2, minus 1, and 1, 3, minus 1. Okay. Okay, so 1, 1, 1, 1, 2, 3, 0, minus 1. Okay, and then the diagonal matrix will be correspondingly minus 3, 0, 0, 0, 4, 0, and 0, 0, 4. Okay, so since now we know the P, so we need to find P inverse. Okay, so P inverse we can perform the row operations. So for example, 1, 1, 1, 1, 2, 3, 0, minus 1, minus 1, and then 1 augmented matrix. Okay, 0, 0, 1. Okay, and then we can perform the row operations, and then finally we will get this. I will not perform those intermediate steps. So finally we will get this augmented matrix, reduced form augmented matrix. 1, 0, 1, 1, minus 1, minus 2, and then minus 1, 1, 1. Okay. So, so now we have P inverse also. So P inverse will be this matrix. So P inverse will be then 1, 0, 1, 1, minus 1, minus 2, and 1, 1, 1. And then we can find A by P times D times P inverse. Okay, I will not find it over here, but now you only need to multiply these matrices. So A P by D. So we know P by D, and then multiplied by P inverse, and then we can find A matrix A. So this is a reverse process. Okay. So one process is if you have A, then you can find P, D, P inverse. And another process is that if we know the eigenvalues and the eigenvectors, then you can find the corresponding matrix A as well. So in this way, the final answer for A will be, the final answer for A will be, in this case, the final answer for A, maybe I can write it over here. Okay, A will be so once you will multiply it, so the final answer for A will be minus 3, 0, minus 7, and minus 7, 4, minus 7, and then 0, 0, 4. Okay. So this way. So with this, I complete the topic of the diagonalization. Okay. Next, maybe is an optional topic, which is about the complex eigenvalues and eigenvectors. So maybe we can start it. So, for example, up to now, whatever the we have chosen those matrices in such a way that we are finding the real eigenvalues, but that is not always the case. We can, depending on the values of the matrix, we can find the complex eigenvalues as well. So the topic is complex eigenvalues. Okay, complex eigenvalues and eigenvectors and corresponding eigenvectors. So corresponding eigenvectors may or may not be complex. Okay, eigenvectors. So first of all, let's have some short review of the complex numbers. Okay, so complex numbers are, as you know, that complex numbers are those which include the square root of -1. Okay, it is called as it is represented by I and spoken as iota. Okay, so as an example, let's see if we have a complex number z is equal to 1 plus iota. Okay, 1 plus iota, which is iota, which is under root -1. And if we have another complex number, w is equal to 2 minus 3 iota, 2 minus 3 iota. So can we do these operations? So for example, then can we find z plus w? So what will be z plus w? Z plus w will be 1 plus iota plus 2 minus 3 iota. So for the addition of the complex numbers, so we add the real part of the complex number with the real part of the other complex number, and we add the imaginary part of the other number with the imaginary part of the other number. So a complex number has two parts, real part and the imaginary part. Okay, so imaginary part is the one with the this iota, and the real part is the one without iota, that is the real number. So in this case, z plus w will be 3 minus 1 iota minus 3 iota, that will be 2 iota. So 3 minus 2 iota. What will be 2 times z? So 2 times z will be 2 times 1 plus iota. So 2 will be multiplied by the real part 2, and 2 will be multiplied by the imaginary part 2 plus 2 iota. Okay, and then number 3, what will be z times w? So in this case, z and w are both the complex numbers. So how we can multiply the complex numbers? So the process is similar to the multiplication in the for the algebraic expression. So what z is 1 plus iota, and w is 2 minus 3 iota. So it will be, we take 1 over here and then multiply it with 2 minus 3 iota. And when we take iota from the first one and then multiply by 2 minus 3 iota. So it becomes 1 times 2 is 2. It is 1 times minus 3 is minus 3 iota. And then it becomes 2 times iota is 2 iota. And then it becomes minus 3 times iota square. Okay. And now you remember, now you know that, I think you know that, understand that iota square is equal to -1. So this will become 2 minus 3 iota plus 2 iota. So it will be 2 minus iota. And then minus 3 into 1. So it will be plus 3 minus 1. So iota square is -1. So it will be plus 3. So finally it will become 5 minus iota. So it will become 5 minus iota. So multiplication of these two complex numbers is also a complex number. But of course, it is not always the case, depending on the components. Next is the next is the modulus of iota. Okay. Yeah. Modulus. So what is the modulus of iota? Sorry, modulus of the complex number, not the iota. So part 4. If we say that the find the modulus of z. So modulus of z is nothing but the length of the complex number. Okay, in the i's in the plane. Okay, so for example, z complex the modulus of z will be equal to because z is equal to modulus of z will be equal to 1 plus iota modulus, okay, or the length. So it is equal to the square root of 1 square plus iota square. Sorry, not iota square. So it will be this 1 square, which is the this real part, and the coefficient of this imaginary part. Okay, so coefficient of this imaginary part is iota. This is 1 iota, so it will be 1 square. So it will be under root of 2, square root of 2. So this is the modulus of iota. And then the fifth part is what is z bar. Okay, z bar is actually the it is the conjugate. Okay, z bar is called as the conjugate of z. Conjugate. So it is z times the z bar. So z bar is the conjugate. So what is the meaning of the conjugate? For example, if z is 1 plus iota, so the conjugate of z will be 1 minus iota. That means you will change the sign of the imaginary part. Okay, so it will be 1 minus iota. So that will be z bar. So it is a form of a plus b into a minus b. So it will be 1 square minus iota square. So 1 square is 1, iota square is minus 1. So minus minus plus, that will be equal to 2 in this case. Okay, so this is the thing. Now, one more thing. So Vi, so what is the value of 1 over W? Okay, 1 over W. So 1 over W is 1 over 2 minus 3 iota. Okay, so this answer is correct. But normally, what we do is we do some simplifications so that in the denominator we don't have the complex number. So for this, we multiply this by the conjugate of this value in the denominator and then divide by the same number. So in this way, we get is 2 plus 3 iota, and then in the denominator we get 2 square minus 3 iota square. So is equal to 2 plus 3 iota, and then it is 4, and then this will be because this will be 9 iota square, so that will be minus 9, minus minus plus minus and minus, so it will be minus, and then this will be minus 9. Okay, and then it will be 2 plus 3 iota over 13. 2 plus 3 iota over 13. So in this way, we have rationalized the denominator. Okay. So this was about the some basic theory about the complex numbers. Okay, is it clear?
Yes.
Yes. Any questions?
No question.
Hmm. Okay. Okay. So the next example will illustrate the polar form of complex numbers. Okay, polar form of complex numbers. Okay, polar form of complex numbers. The polar form of complex numbers is uh, so for example, if if we have a complex number z is equal to a plus b iota. Okay, so we can represent its modulus z as like this: a square plus b square. Okay, and if we say that if its modulus is equal to r, if modulus of z is equal to r, okay, then uh, we can write the angle of which this z makes. So for example, if we represent it in the real and the imaginary coordinates. So if on the real axis it is a, and on the imaginary axis it is b. So it is a and then b over here. Okay, so in this way we can represent this number, and then this when we will talk about the polar axis, polar coordinates. So this distance will be r. Okay, and then the angle which it will be making with the real axis, that will be theta. So this angle is represented by the term which is called as the argument of z. It is the angle which the vector makes with the x-axis. Okay, so angle, it is the angle which the vector makes with the x-axis. Okay, which the what is the vector in this case? The vector uh, is called 1 RB. Okay, so which is the angle theta, which is this angle is called as the theta. So then we can represent this z as equal to r cosine theta plus iota r sine theta. Okay, so this complex number can be represented like this. So in this case, if for example, if we have a complex number, z is equal to under root 3 plus iota. So where under root 3 is a real number, irrational real number, and iota is a imaginary part. So if we want to find its polar coordinate, so first of all, so we want to convert to polar coordinates. convert it into polar coordinates. So for the first step is to find the modulus of z. So modulus of z will be equal to square root of 3 square plus 1 square. So it is equal to 3 plus 1, that is 4, that is equal to 3. And then we will find the argument of z. Okay, argument of z. So what is the argument of z? So argument of z is this angle theta. And then this angle theta we can find by, because this is side B. If we take a simple triangle, this is side B, this is side A. So that will be equal to the tangent inverse. Okay, that will be equal to the tangent inverse B over A. So B in this case is 1. And A in this case is 1 over under root 3. So tangent inverse 1 over under root 3 is equal to the, this is about 30 degree angle. 30 degree means it is pi by 6. Okay, it is pi by 6. So tangent inverse 1 over under root 3 is pi by 6. So in the polar coordinates, then we can represent it like this. R is 2 cosine of pi by 6 plus iota sine of pi by 6. Okay, so in the polar coordinates, we can represent like this number. So whenever we want to represent a complex number into the polar coordinates, so first find its modulus, then find its argument. Okay, so modulus is basically the length of that complex number. Argument is the angle of that complex number with the real axis. And then we can represent it like this. So there is a theorem which is called as the de Moivre formula or theorem. Okay, formula, which can be proved as well. So what that formula says is that cosine of theta plus iota sine of theta power k. Okay, cosine of theta plus iota sine of theta power k is equal to cosine of k theta plus iota sine of k theta. So which we can see that it's very convenient in this case. So in this case, what we know, maybe we can apply this formula over here. So first we know that if we have z is equal to like this, in this case, we have under root square root of 3 plus I. So if we want to find z square, that means z times z. So it will be equal to under root 3 plus iota square. So it will be under root 3 plus square is 3 plus iota square, it will be -1, and then plus 2 under root 3 iota. Okay, so it will be 3 minus 1 is 2 into 1 plus under root 3 iota. So we will get from here. Or if we apply this formula for the polar situation, okay. So for the polar situation, what we can get is, because from this, it is of this form, cos theta, okay, and plus iota sine theta power k. So it will be cos sine of, that is k in this case of 2. So it will be cosine of 2 times of this plus iota sine of 2 times of this. So in this case, z square in the polar coordinates, it will be equal to 2 square. Okay, 2 square into cosine of, instead of pi by 6, it will be k pi by 6, okay, or k was 2, so it will be cosine of pi by 3, and then iota sine of pi by 3, okay. So now we know that this is 4, and cosine of pi by 3 is cosine of pi by 3 cosine of 60 degree is equal to 1 by 2, right? Sine of 60 degree is equal to 1 by 2, or yes, 1 by 2, and plus iota sine of 60 degree is equal to under root 3 by 2. So this simplifies into, because 2 cancels with this 4, so it will be 2 into 1 plus under root 3 iota. So which is the same answer which we got before. But in this case, remember that this formulation will be very convenient if we want to find a very higher power of k. So for example, if you want to find z to the power 5, okay, so then what we can do is we can convert z into its polar coordinates, and we can use this formula, and then we can very easily find the value of, because it will be then 5 times this, and then from here we can very easily find the value. But otherwise, if we will apply this simple situation, then we have to multiply 5 times with z with each other, and then that will involve a lot of calculations. So this is the use of the this is the usefulness of the polar coordinates. Okay, so is it clear?
Yeah.
Yes.
Yeah. So the advantage of the converting a number, advantage of converting a complex number into its polar coordinate is that we can easily find the higher powers of that complex number. So with this thing in mind, then we can find the, but now we have almost reached to the end of the lecture. But let's spend a few more minutes. So for example, if we now have a matrix example, okay. If we have a matrix A as 2 minus 2, 3, 2. So we want its eigenvalues and eigenvectors. So for eigenvalues, what you will do is we will write it like 2 minus lambda minus 2, 3, 2 minus lambda. Okay. And then we find its determinant. So 2 minus lambda square minus 2 into 3, that is equal to 0. This is the characteristic equation. So this characteristic equation will be simplified into lambda square minus 4 lambda plus 10 is equal to 0. However, for this characteristic equation, there is no real solution. And from the quadratic formula, okay, from quadratic formula, we can find that its two solutions are 2 plus minus under root 6 iota. Okay, so this will be the characteristic. These will be the two eigenvalues. Sorry. And then from if we have found these eigenvalues, the process is the same as was for the real values. So we take this 2, and then we will subtract the first eigenvalue. So minus 2 minus 6 iota, and then minus 2, and then 3, and then it will be 2 minus 2 minus 6 under root 6 iota. So what we get over here is minus under root 6 iota minus 2, and then 3, and then minus under root 6 iota. And then for the eigenvectors, then it by the row operations, it is minus under root 6 I minus 2 0 0 and then 0 0 0. So from here, what we get this first eigenvector as u1 is equal to 2 minus under root 6. So I am skipping some steps in between, but these are very easy and then very similar to the case of the real. So that will be the first eigenvector. And applying the other conjugate value for the complex number, the second eigenvector will be simply 2 under root 6 iota. Okay, so we can verify it. So for example, if this is then eigenvector or not. So for example, if we take 2, 3 minus 2, 2, and then we take multiplied by 2 minus under root 6 I. So it will be 2 into 2, 4 minus 2 into 6. So it will be plus 2 under root 6 I. 2 into 3 is 6 and minus 2 under root 6 I. So from here, what we can do is we can take 2 as common. Okay, we can take we can take 2 plus under root 6 I as common. Okay, 2 plus under root 6 I as common. So it will be what we have left over here is 2 plus under root 6. So what we will be left over here is 2. And then what we will be left over here is, so to understand it better, okay. So 4 plus 2 under root 6 I, what is this? 2 into 2 plus under root 6 I. And then over here, what we have over here is 3. Sorry, 2. We have 2 also as common. So we have 2 under root 2 as common. So we have over here is 3 minus under root 6 I. 3 minus under root 6 I. So so what I wanted to do was that I want so I had this matrix 2 minus 2 2 minus 2 3 2, and then what I found was that 2 under root minus under root 6 I, and then I multiplied it. So 2 times 2 is 4 minus 2 times 6 is plus 2 under root 6 I, and then 3 times 2 is 6, and that is minus 2 times under root 6 I. So from here I took 2 as common, so it was 2, and then under root 2 plus under root 6 I, and then 3 minus under root 6 I. So what is this? So I can take 2 as common, so it will be 2 plus under root 6 I, and then it is 3 minus under root 6 I. Okay, so this is A, this is U, and then for the eigenvector situation, what we should have is AU is equal to lambda U. Okay, so lambda, what was lambda? Lambda was 2 under root 6 I. Okay, so and then U is this one. Yeah, I think maybe we can. I don't have time, but I think we can prove it. So we may be able to take this 2 plus under root 6 I as common, and then it will be inside. It will be 2, and this can be proved like this. So I think I will leave it to you. So 2 plus under root 6i. Okay. 2 plus under root 6i, that will be common from this matrix. Okay, take this common, and then inside you will get this 2 into minus under root 6i, that which was the U matrix. So I leave it to you to verify it. Okay. Okay. So in this way, then this will prove that we have the eigenvector which we have found is the correct one. Okay. Anyway, this can be proved. Okay. So any questions?
No question.
No question. Okay. Only 14 participants. Okay. So the assignment is also there. So Mathematica assignment is Mathematica assignment number 4 is due next week. Okay. So okay, that's all for today. So I shall see you on Monday.
Yeah. Goodbye. See you.
Thank you. Goodbye.